Energetics 7a, Entropy and Spontaneity. The essential idea: a reaction is spontaneous if the overall transformation leads to an increase in total entropy, that's the system plus the surroundings. The direction of spontaneous change always increases the total entropy of the universe at the expense of energy available to do useful work. This is known as the second law of thermodynamics, nature of science. Theories can be superseded. The idea of entropy has evolved through the years as a result of developments in statistics and probability. Spontaneous processes. What does spontaneous mean to you? I guess in common parlance, people think of spontaneous as something happening immediately or at this instant. In chemistry, we think of it a little bit differently. Examples of spontaneous chemical reactions, for instance. This young lady heading down a hill on the bike, that is going to occur without adding more energy. Diffusion. This solid, this purple or pink solid at the bottom of this beaker of water is going to move through, dissolve through this solution without adding any more energy. These nails are going to rust without external forces adding energy. And this reaction here is an example of a reaction taking place without the need for a constant supply of energy. Spontaneity does not refer to the rate. For instance, obviously this rusting goes on, it takes forever. And this looks like a pretty fast reaction, but they're both spontaneous. Examples of non-spontaneous processes. This egg, it's not going to become fried or boiled or cooked on its own. You'd have to add heat for it to change. Here, you've got two wires in a solution. If the other end of the wires were attached to either end of a battery, so there's a potential difference between the two wires, then you get a flow of ions between them. Without that battery to provide the difference, or the potential difference, or the voltage difference, then your ions aren't going to flow between the two. Here you've got some bloke pushing a boulder up a hill. Obviously he's providing the work there. He's providing the energy for that to happen. It wouldn't happen spontaneously. And finally, you've got this nice little plant growing there, and that is going to stop growing if light isn't constantly provided, if a source of energy isn't permanently there. So what is a spontaneous process? Well, it occurs without outside intervention or the need to do work once it's started. And it moves from a less stable to a more stable state. What factors contribute to the stability of a chemical system? Well, the energy change, or enthalpy change as we know it, and the entropy change, the amount of disorder. Exothermic reactions, as we know, have a negative change in enthalpy. The reactants have a greater enthalpy than the products. So the enthalpy of products is lower than the reactants. Endothermic reactions have a positive enthalpy change, and the enthalpy of products is greater than the reactants. In energy terms, a state of low energy is more stable than a state of high energy. Therefore, reactions that produce products with lower energy than the reactants are more likely to be spontaneous. In other words, exothermic reactions tend to be spontaneous, endothermic reactions tend to be non-spontaneous. Consider this: you have an ice cube melting. The ice has a lower enthalpy than the water, which has a higher enthalpy, and so going from the ice cube to the water is endothermic. And so, like we just said here, the endothermic reactions tend to be non-spontaneous, so we would assume this would be non-spontaneous according to that rule. But as we know, it very much depends on temperature, and we will get to that. Entropy and spontaneity. You can see this little cartoon of a man sitting in the Department of Entropy in the place is a mess. If you think about your own bedroom, it will just tend towards disorder if you don't put the energy in to keep tidying it. And this is the nature of the universe. And so if anybody ever complains about the state of your bedroom, you can tell them that you're fighting an unwinnable fight against thermodynamics. A simplified description of entropy. Entropy is a measure of the disorder or randomness in a system. The symbol is S with our nice little circle at the top there, and joules per Kelvin per mole. Ordered states have low entropy and disordered states have high entropy. Which one has greater entropy, ice or steam? That's right, steam. Which has greater entropy, sugar dissolved in tea or sugar cube? Which is more disordered? Again, you're correct, it is the sugar dissolved in tea. Your chemical notebooks, the way you have it or the way Miss Berry would like it? Well, that depends. If it's Fred's, this wouldn't work, but for other people, then it's the way you have it is probably more disordered than how Miss Berry likes these things. And a deck of cards in a pile or after 52 card pickup? Of course, after 52 card pickup. 52 card pickup is, if you don't know it, it's where you say you want to play a game of cards. The person says yes. Then you say, do you want to play 52 card pickup? If the person says yes, you just throw the cards in their face and they've got to pick them up. Entropy and spontaneity. Indicators of increasing entropy in a reaction. Moving from a solid to a liquid or gas shows an increase in entropy. Liquid, the particles are far more disordered than they are in a solid, and in a gas they're even more disordered. Moving from an ionic crystal, which is very ordered, to dissociated ions in a solution where they're free to move around, obviously more disordered. Moving from a molecular form to a dissociated form, so as you can see this ethanoic acid moving to its two ions, there's more disorder. And finally, an increasing number of particles in the same state. So you've got two gas molecules here. Once the reaction has taken place, you've got three gas molecules. So this is more able to be disordered. There's more of it to be disordered. Which reaction shows an increase in entropy? Well, we've got 1 mole of this thing here, and we've got a mole of this. So there's 2 moles of stuff over here, 2 moles of particles. So that's definitely an increase in entropy. Here we've got 12 gas particles, 6 liquid particles. Over here, just 1 solid and 6 gas. So I've got 6 gas to 6 gas. There won't be an increase in entropy there. Oh, sorry, just kind of spoiled it for you. Well, we're going to do it anyway. Gas to liquid obviously is less disordered. A gas is more disordered than liquid. Here we've got gas to gas to gas, but we've got 3 moles of gas particles at this side and only 1 mole that side. So it's more disordered here. And finally, as you saw when I pressed that button accidentally, I've got 2 moles of gas particles here going to 4 moles of gas particles here. So this is going to become more disordered. So there will be an increase in entropy. Entropy and spontaneity. Spontaneous reactions tend to go to a greater state of entropy. They have high entropy. Entropy changes of reactions. The symbol for entropy change, as I said, delta S. The definition of the change in entropy is the change in entropy equals the change in entropy of products minus the change in entropy in reactants. If the change in entropy is negative, this means there's a decrease in the entropy of the system. If the change in entropy is positive, this means there's an increase in the entropy of the system. Can you predict the signs of the following values? Press pause and have a go, please. Okay, let's see if you've got them right. We've got an increase here, 2 moles over here, coming from 1, and this is a solid as well. So we've got these dissociated ions moving through. There's more entropy. Then we've got a gas and a gas going to a solid and a gas, and there's 6 gases there, 6 gases there, but we've got these liquid molecules. So it's going to be, there's more entropy this side, so it's going to be negative. Next, gas to a liquid. That's right, negative. Nitrogen and hydrogen, gas, gas, gas. But like we said before, 3 here, 1 there, so it's going to be negative. And finally, increase in entropy, like we talked about, so that's going to be positive. Good. How do we calculate the entropy change of a reaction? Well, consider this general equation for a reaction. First of all, you've got the coefficients, lowercase, and you've got reactants, uppercase. The change in entropy is going to be the sum of the entropy of the products subtract the sum of the entropy of the reactants. Okay, and so you just find the entropy of this and this, add them together, and subtract the entropy of these two reactants. Let's do one of those. Calculate the value of the change in entropy for this reaction. It's the ammonia turning into hydrogen and nitrogen. The standard entropies are as follows. So we'll just plug them in. We're going to put the hydrogen, which is 131, and it's 3 of them, so 3 times 131, plus the nitrogen, and the nitrogen is 192, there's only one of them, subtracted the reactants, which is ammonia, which is 192 times 2. Just do the maths and make sure you get those units right for entropy, joules per Kelvin per mole. Example 2. Predict and explain if the following reaction will have an increase or a decrease in entropy. Well, if we can see, it is gas, gas, going to a gas. So there's 2 moles of gas over here, 1 mole of gas there. So it's going to be a decrease in entropy. So it's going to be negative. And now we can use the entropy change of the reaction using the values in table 12 of the data booklet just to check. And it is indeed negative. So do the sum of the products, which is just 1 here, which is 230 for the ethane, and then subtract the sum of the entropy of the reactants, which is 220 for ethene and 131 for hydrogen. Gives us minus 121 joules per Kelvin per mole. Oops, sorry, just shift this along. Oh no, I don't need to shift it along, because that is in fact the end of this presentation. Splendid.